Ever feel like the AI around you is, I don't know, doing more? Not just answering, but acting.
Yeah, it's definitely shifting. We're really moving into this era of what people are calling AI agents.
AI agents. So systems that aren't just waiting for us, but can act on their own.
Exactly. It's a fascinating shift, isn't it, from passive tools to more active participants,
Yeah.
things that can perceive, decide, and then do
Yeah.
something, in their environment.
Right. And that's exactly what we want to unpack today. Really get into what AI agents are, how they tick, why they're such a big deal, and maybe touch on some more advanced stuff too.
And we've got a great guide for this document, AIagents.pdf. Does a pretty good job breaking it down.
Yeah, it looks really helpful. So the plan is start with some easy analogies, nail down the core ideas, look at the mechanics, different types, and then sort of zoom out to the bigger picture.
Sounds like a good plan. A way to get up to speed quickly without drowning in jargon.
Hopefully. Think of it as your shortcut. Okay, so let's dive in. Maybe start with those analogies. What are some simple examples to help us get a handle on this?
Well, a really simple one is a smart thermostat.
Hmm.
It senses the room temperature. That's the perception bit.
Okay,
Then it decides, okay, it's too cold, and turns on the heat. That's the action, all by itself.
right. Perceive, decide, act.
Or like a robot vacuum cleaner, a Roomba. It uses its sensors to map the room, avoid bumping into things, figure out where to clean next.
Autonomously, that's the key word, isn't it? Purposeful interaction.
Precisely. It's not just passively sitting there. And, it's interesting. Bill Gates was talking about software agents way back in the 90s, thinking of them as information filters.
I remember that.
Yeah.
But today's agents feel different, more capable.
Oh, absolutely. It's a huge leap. Thanks mainly to modern AI, especially things like large language models, LLMs. They give these agents much more sophisticated reasoning planning.
So they're not just finding information, they're actively doing things to achieve goals for us.
That's the core shift from assistance to actual agency. And as the source points out, this raises some big questions, doesn't it? Societal, ethical.
Yeah, the document mentions some pretty provocative analogies, comparing them to corporations or even, well, entities without empathy or maybe too compliant. Just as thought experiments, of course.
Right. They're just analogies to make us think about the potential impact,
Yeah.
which underlines why we need to understand them. So let's get that core definition down. What's the standard one?
The source uses the classic Russell and Norbig definition, which is pretty much the gold standard. Anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators.
Okay, let's break that down. Perceiving through sensors. What kind of sensors are we talking about?
Mhm.
Can be physical, right?
Totally. Cameras, microphones, GPS, temperature sensors, like on the thermostat, but also virtual ones.
Virtual? Like what?
Like keyboard input, reading data from an API, scraping info off a website, anything that gives the agent data about its environment.
Got it. And the acting through actuators part, that's the doing part.
Yeah, that's how it makes changes. Physically, it could be motors, robotic arms, speakers, moving or making sound,
And virtually.
generating text, sending an email, calling another API, displaying something on screen, anything that affects its digital surroundings.
So it's this constant loop. Sense, think, act. Sense, think, act.
Exactly. And the environment is just everything outside the agent it interacts with, the stage it acts on.
And crucially, this definition is about behavior,
Right.
what we can observe. It's not saying they're conscious.
Precisely. The focus is usually on rationality. Does it do the right thing, the effective thing, to reach its goals, not about feelings.
Makes sense.
Yeah.
So why is this such a big deal now? Why this shift towards autonomous AI? What makes these agents significant?
Well, the source lays out a few key properties. First, autonomy operating without needing us constantly holding their hand.
Dependence.
Then, rationality trying to make the best choices to achieve their goals based on what they know and see. Reactivity or adaptability is huge too, responding to changes, but also proactivity, taking initiative, not just reacting.
And the big one, learning.
Yes, learning from experience to get better over time. That's a massive capability for many agents.
And it's this whole package deal, autonomy, rationality, reactivity, learning, that lets them tackle really complex, multi-step jobs, right?
Exactly. And the fuel for this, as the source emphasizes, is those big foundation models, GPT, Claude, Gemini, those guys. They provide the the advanced reasoning and language
The
skills.
brains for a lot of these newer agents.
Pretty much. And we're also seeing frameworks like LangChain, AutoGen, Crew AI pop up. They make it easier to actually build these agents using those powerful LLMs.
So the tools are getting better too, making
Yeah.
it more accessible.
Definitely. Okay, so we know what they are, why they matter, how do they actually work. Let's get into the mechanics.
Right. We've touched on sensors and actuators, the inputs and outputs.
And the specific combination really defines what an agent can do, doesn't it? A self-driving car needs cameras and LiDAR. Its actuators are steering, brakes.
Whereas a calendar agent uses APIs for both sensing appointments and acting to schedule new ones. Different tools for different jobs.
Exactly. Like you said, a robot with no eyes won't navigate well. The sensors limit perception, the actuators limit action.
Okay, what about the world they live in, the environment? The source breaks this down into different dimensions. That seems important for design.
Yeah, super important. First is observable or partially observable. Can the agent see everything relevant?
Like chess is fully observable, you see the whole board. But driving in fog, not so much.
Exactly. Partial observability means the agent needs memory or an internal model of the world to keep track of what it can't see right now.
Okay, what else? Deterministic versus stochastic.
Right. Is the outcome of an action certain deterministic, or is there randomness involved?
Yeah.
Stochastic. Flipping a coin is stochastic. Most real-world stuff has some randomness.
Makes sense. Then episodic versus sequential.
Does each decision stand alone? Episodic, like classifying single images. Or do actions have consequences down the line? Sequential, like in a game or a long conversation.
Sequential seems much harder, needing planning.
Definitely. Then static versus dynamic. Does the world stay put while the agent thinks, or is it changing?
A crossword puzzle is static. Traffic is very dynamic.
Right. Dynamic environments demand faster reactions than discrete versus continuous.
Finite options versus infinite, like a light switch, discrete versus steering a car, continuous.
Exactly. Continuous spaces are often trickier. And finally, single agent versus multi-agent.
Is it alone? Or are there other agents interacting, maybe cooperating, maybe competing,
Yeah.
like robots on a factory floor or players in a game?
And the source points out real-world problems often have the toughest mix: partially observable, stochastic, sequential, dynamic.
The hard stuff. Okay, so given all that complexity, how does the agent actually decide what to do? The thinking part.
That's the decision-making engine and the knowledge base. The core idea is the agent function mapping perceptions to actions.
How does it do that mapping?
Well, simple agents might just use if-then rules. But smarter ones have a knowledge base storing facts, rules, learn stuff, models, goals.
And they use different algorithms for deciding.
Yeah, a whole toolkit. Simple rules, search algorithms to find paths to goals like GPS routing,
Oh.
planning algorithms to create action sequences, machine learning for pattern recognition, reinforcement learning, trial and error, learning from rewards.
Like training a pet?
Kind of. Utility theory for weighing preferences and handling uncertainty. And then more complex stuff like neural networks, Bayesian methods.
Wow, quite a range. But the goal is usually rationality, right?
Hmm.
Making the best choice given its goal and what it knows.
That's generally the aim. Now, to structure all this thinking, the source introduces the PEAS framework. PEAS.
Right, P's, what's that stand for again? Performance, environment.
Performance measure, environment, actuators, sensors. It's a structured way to define the agent's task and context before you build it.
Okay, so P, performance measure. How do you measure success?
Exactly. Is it winning a game, getting you there fast, diagnosing accurately, keeping the room comfy? You need a clear metric. I heard a funny story once about a vacuum bot optimized for area cleaned per minute.
Oh no.
Yeah, it just cleaned one corner really, really fast, didn't clean the room. Bad performance measure.
Huh. Okay, shows why defining it well matters. E is environment. We've covered that, the context.
Right. The characteristics, observable, dynamic, etc.
A is actuators, what the agent can do. Steering, emailing, moving a piece.
Yep. And S is sensors, how it perceives. Cameras, APIs, keyboard input.
So P's is like the blueprint. Define these four things first.
Crucial first step. The source gives examples like an automated taxi and a medical diagnosis system, showing how different the P's specs are for each.
Right. Safety for the taxi, patient health for the diagnosis system, different goals, different environments, different tools. Makes sense.
All right, so that's the core concepts and mechanics. Now, what about the different types of agents? The source lays out a kind of hierarchy.
Yeah, starting with the simplest. Simple reflex agents.
The thermostat type. Just react to the current input based on rules. No memory.
Exactly. Condition action rules. If temp low, turn on heat. Simple, fast, cheap. Good for predictable worlds.
But limited. Can't handle anything new or remember the past, like an automatic door doesn't know if you just went through.
Precisely. So the next step up is model-based reflex agents.
These have memory, or a model.
Kind of, yeah. They maintain an internal model of the world, tracking things they can't currently see. They update this model based on perceptions and how actions affect the world.
So, the self-driving car remembering the truck that went behind a building, using its internal model.
Perfect example. It helps them handle partially observable environments. More flexible, but building that model is harder.
Okay. Then, goal-based agents.
Now we're talking objectives. These agents have explicit goals and use search or planning to figure out action sequences to reach them.
Like the GPS finding a route, or a game AI planning moves ahead.
Exactly. They're more flexible, change the goal, change the behavior. But planning can be computationally heavy.
Makes sense. What about utility-based agents? How are they different from goal-based?
They go a step further than just reaching a goal. They have a utility function that rates how good different states or outcomes are. They choose actions to maximize this expected utility.
So not just get there, but get there balancing speed, cost, and maybe scenery. Or like a trading bot balancing profit and risk.
Exactly. They handle trade-offs and uncertainty better, more rational in complex situations. But defining that utility function, that's tricky.
I can imagine. Okay, finally, the most advanced. Learning agents.
Right. These are the ones that improve over time through experience. They don't just rely on pre-programmed knowledge.
Like the Netflix recommendations getting better as I watch more.
Classic case. The source mentions 4 parts. The learning element figures out improvements. The performance element acts. Could be any of the other agent types. The critic gives feedback. And a problem generator suggests exploring new things.
So they can adapt to unknown environments, maybe find solutions designers didn't even think of.
That's the power. But they need data, time to learn, and sometimes their learned behavior can be unexpected.
Right. The source has a comparison table too, which sounds useful for keeping these straight.
Yeah, definitely check that out. Good summary of strengths, weaknesses, examples.
Okay, this is all great for understanding agents, but the source talks about AI literacy. Why is knowing about agents so important for just general AI literacy?
Well, these agents are becoming so woven into everything, right? Understanding them helps us use AI tools better, knowing what they can and can't do.
Makes sense. For work, too, probably.
Absolutely. Working alongside AI. Plus, it helps critical thinking, questioning AI results, spotting bias, knowing how a decision was potentially made.
And engaging in bigger discussions about AI's impact.
Exactly. And protecting ourselves, understanding data use, privacy, it's becoming fundamental. The source recaps those core ideas: autonomy, perception, action, goals, decision-making, learning. Getting those helps demystify agents.
But literacy isn't just about understanding. It's also about thinking critically, about the downsides.
Definitely. We touched on bias agents learning bad patterns from data. Transparency issues, the black box problem. Reliability, sometimes they fail unexpectedly, or LLMs hallucinate. Security risks, like prompt injection.
Yeah, those are serious concerns, and ethical ones, too.
Big time. Accountability, who's responsible when an agent messes up. Privacy concerns with all the data they collect. Potential for misuse.
And there are just inherent limitations, right? Things they aren't good at.
For sure. Deep context, true creativity, emotional intelligence, complex social stuff, high-stakes ethical judgments, unpredictable physical worlds, they still struggle. Healthy skepticism is good.
Okay, so we've covered single agents pretty thoroughly. What about beyond single agents? The source mentions multi-agent systems, MAS.
Right, so sometimes one agent isn't enough. Think complex problems like traffic control or coordinating robots in a factory or managing a smart energy grid.
Too big for one brain.
Exactly. So
Yeah.
a multi-agent system has multiple agents interacting in the same environment. They might cooperate, they might compete, they might just coexist.
What are the benefits of using multiple agents?
Several things. You can break down huge problems. Agents can work in parallel, speeding things up. It could be more robust. If one agent fails, others might carry on. You can have agents with different special skills. They can be spread out geographically.
But getting them to work together sounds challenging. Coordination, communication.
That's the tricky part. How do they share info? Avoid conflict. Negotiate. The source mentions different ways to organize them: centralized control, decentralized peer-to-peer, hierarchies. It's complex. Waymo's Carcraft traffic simulation is a good example mentioned.
And this interaction can lead to unexpected things, emergent behavior.
We'll get to that, but first, how do they talk? Agent communication languages, ACLs.
Why special languages? Can't they just swap data?
Sometimes raw data isn't enough. For real coordination, they need to understand the meaning and intent behind messages. ACLs provide standard ways to do that, like a shared grammar for agents.
And the source highlights one called FIPA ACL, based on Speech Act theory. What's that?
FIPA ACL is a big one. Speech Act theory basically says that when we talk, we're doing things with words. Asking a question is performing the act of requesting information. Making a promise is performing the act of committing.
Ah, okay. So ACLs define these communicative actions.
Exactly. FIPA ACL has performatives like inform, request, propose, agree, refuse. It standardizes the message structure, who sent it, who it's for, the performative, the content, the language used for the content, a shared vocabulary or ontology.
Wow, very structured.
It needs to be for reliable communication between potentially very different agents. It provides that formal semantic framework.
Okay, really sophisticated. Now, back to that emergent behavior idea. What happens when these agents interact?
Right. Emergence is when complex, surprising, system-level patterns arise just from the simple interactions of individual components. The overall behavior wasn't explicitly programmed.
Like the flock of birds analogy the source uses. Simple rules for each bird lead to complex flock patterns.
Perfect example. Each bird isn't thinking about the flock's shape, just its neighbors. But the beautiful patterns emerge. We see this in AI too.
Where?
Big language models developing abilities like reasoning or translation that were specifically coded in, but emerged from this scale and training, sometimes called emergent abilities.
So the whole is greater than the sum of its parts, sometimes unexpectedly.
Exactly, which can be amazing innovation, adaptability, finding novel solutions, but it's also risky.
How so?
Unpredictability. Can we control it? Is it safe? Ethical? Undesirable behaviors can emerge too, and it's hard to debug or know why it happened. Who's accountable? It's a huge challenge, harnessing emergence while keeping things safe.
A major research area, I bet. Okay, one last advanced topic, prompt engineering for agents. We hear about prompting for chatbots, but how does it apply here?
Well, even these autonomous agents often need a good starting point, clear instructions. Prompt engineering for agents is about crafting that initial input to guide their entire operation. It's more than just a question.
So, setting the stage properly, defining the mission.
Exactly. Defining the goal clearly, guiding the planning, maybe suggesting steps using chain of thought, giving it a role or persona, providing necessary context or data, telling it which tools to use and how, specifying output formats, even coordinating prompts across multiple agents.
So the prompt is like the high-level strategy document for the agent.
That's a good way to put it.
Yeah.
It's crucial for reliability, accuracy, and making sure the agent actually does what you want it to do. It's the main way we interface with and direct these powerful systems, even with their autonomy.
Wow. Okay, we have really covered a ton today. From simple thermostats to multi-agent systems, speaking their own languages and exhibiting emergent behavior.
It's a huge landscape. And like the source document says near the end, this is really just scratching the surface, isn't it?
Absolutely. Things are moving so fast. Grasping these concepts is step one, but staying curious and continuing to learn is key.
Which brings us to a specific point the source makes, directed right at you, the listener.
Yeah. What's that?
It explicitly recommends, and I'm quoting here, you should absolutely follow this book series and read the next book to deepen your understanding and get more hands-on experience.
Ah, so encouraging further reading. And it mentions where to find it.
Yep. Points out that it's available for reading on Amazon. They really emphasize moving beyond just theory.
That makes sense. You can't really get this stuff without trying it out, can you?
Exactly. The source actually says if you stick only to theory, you will forget. You need to apply it, maybe build some simple agents, do some dummy projects to really make that knowledge stick and turn it into a skill.
Solid advice. Make it practical. Okay, so a final thought to leave everyone with. As these agents get more capable, more autonomous, maybe think about how they're already showing up in your world. Can you spot the different types? The simple reflex ones, maybe some learning agents in your apps?
Yeah, and how might they change things for you personally or professionally down the road? It's definitely something worth keeping an eye on and continuing to explore.
Absolutely. Keep exploring, keep learning. The deep dive definitely continues.